Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. So this is the emerging topic section of the NIPS 26 tutorial. I hope you all had a good start to the day in the breakfast. So in this session, in the next 2 hours, Jeff Dean and Oriol Bignal will be jointly giving a tutorial on large-scale distributed systems and how to use them for training neural networks. Jeff and Oriol have been at the forefront of inventing and developing algorithms for training neural networks with large-scale computer systems, and they applied these to quite a variety of problems that have traditionally been very, very difficult for computers. They've made significant improvement in the state of the art. In many of the areas, the software systems and algorithms have been used by dozens of different groups within Google. For example, speech recognition, image recognition, and various visual detection tasks, language modeling, language translations, and many, many other tasks that they're going to mention here today. So in the next 2 hours, they'll share all those learnings with us. They demonstrate a recently publicly released TensorFlow open source software system, which is why we have a second screen. And they've put together a deck that makes it, with TensorFlow, they've put together a package that makes it really easy to conduct research in large-scale machine learning. So before we get started, a few words about Jeff and Oriol, both on the professional and on the personal front. So Jeff's no stranger to distributed systems. After receiving a bachelor degree from the University of Minnesota in 1990, he started a PhD in computer science at UW in Seattle, which he completed in 1996 working with Craig Chambers. After 3 years at the Compaq's Western Research Laboratory, he is one of the early employees of a very small startup in the Silicon Valley called Google. At Google, he's currently the senior fellow in the research group where he leads the Google Brain team, and he designed many of the distributed systems that are used and underpin Google systems, and everyone in the room probably knows. Advertising systems, crawling system, indexing the web, and querying serving system. Jeff's probably the most well-known for the invention of MapReduce, but that's just one of the distributed systems that he did, and many others include Spanner, include Bigtable, LevelDB, and more recently, Google Brain and TensorFlow. Jeff got elected to the National Academy of Engineering in 2009, and in 2012 he received the ACM Infosys Foundation Award in Computing Science together with Sanjay Gamawat. When Jeff's not working on training neural networks or inventing distributed systems, then he's working on another life goal of his, and that is to play soccer and basketball in every continent on this planet. So far, he's done it in several. He's done it in North America, he's done it in South America, he's done it in Europe, and he's done it in Asia and Africa. I think Antarctica might be a little tough to complete those. Oriol started his scientific career in 2007, where he completed a dual degree in telecommunication engineering and mathematics from the Polytechnic University of Catalonia in Spain. He completed his undergrad thesis at the Robotic Institute of CMU on machine learning and computer vision, and in 2009 he graduated with a master's degree in computer science and engineering from the University of California, San Diego, and joined Berkeley to work in 3 different areas covered today: speech recognition, signal processing, teleimmersive technologies, and computer vision and machine learning. He graduated in 2013, joined Google working on deep learning, both for image captioning and conversation modeling. And when he's not doing science, he's, I think, the top StarCraft player in Spain. He was the top StarCraft player in Spain, and we mean the original StarCraft. So I think I can't really think of 2 better people to tell you and share their insights with us and tell us about distributed learning of neural networks. And I'm very, very happy when both of them agreed to give this tutorial. So please welcome them to the stage.
All right, thank you. So let's get started. You want to get the screensaver deactivated? Okay, we're going to have dueling things to project most of our slides on both screens. So let me just give you a little bit of background about the kinds of stuff we've been doing for the last few years. In particular, the Google Brain project started in 2011 as a small project with a focus on really trying to apply large amounts of computation and to train very large deep neural networks. At that time, neural networks were starting to show promising results in a number of different areas. And we felt that if we could really scale up the kinds of models that we could train, the sizes of models, and the amount of data we could train on, we could really sort of push the boundaries of what these systems could do. And we started out kind of working in the perceptual domain and then kind of have gradually been moving into other domains, in particular language understanding and other kinds of sort of non-perceptual tasks over the years. So we're going to kind of cover our experience in building large distributed systems from the point of view of doing two things. One is doing research in a number of the different domains that Ralph mentioned, and then also in using those research systems and taking them into production systems across a wide variety of Google products. And this is often in conjunction with many product teams at Google. So our focus in the project has been on neural nets, but a lot of the distributed systems infrastructure we've developed is actually a bit more general than that. It can be used for a wide variety of machine learning methods. But most of this talk will focus on how we've been using it for neural nets. The other part of the talk, we're going to demonstrate TensorFlow, both kind of at the how you would use it as a user of TensorFlow, and also discuss what's going on underneath the covers in TensorFlow and how we think that's a pretty good abstraction for building systems that are easy to express but also easy to scale. And so we'll show a bunch of real examples. There'll be kind of live code happening. We hope it all works. And we'll kind of explain what's happening underneath the covers as we're doing some of those examples. So just to make sure everyone's on the same page, people are probably pretty familiar with deep learning. We're going to do maybe a 5-minute intro to the kinds of things that deep learning does and how it generally works. Then we're going to give you an overview of kind of the basics of TensorFlow and a simple demo and talk about sort of some of the initial pieces of the implementation. Then we'll talk about the work we've been doing to scale up large-scale training systems. And in particular, we'll focus on model parallelism and data parallelism and other kinds of techniques that are really good at making it so that you can train large models quickly. And we'll actually show you how you can express these kinds of different kinds of parallelism in TensorFlow using some more complex examples that we've been developing in our research program. So that left axis is sort of where we started the project of trying to use deep neural nets. And in particular, we initially were doing some research on unsupervised learning, and then we started to work with the speech team a bit to scale the speech recognition system for doing so the acoustic modeling of speech recognition. And I think one of the things this graph illustrates, this is kind of the number of different directories containing model description files for our first deep learning system at Google. And you can see that we have 1,000 different directories that many different teams have developed these model description files to tackle problems in their particular domains. And it's really nice that it's across a really wide variety of different areas. And you can see that once you have a few teams using these things successfully, they kind of spread organically because people will hear from their friends, hey, I tried it for this problem and it worked really well. And so that's kind of why you see this large exponential curve in how many different teams are using these kinds of approaches. And it really is the case that these kinds of models are fairly universal. You can sort of take the same general learning algorithms and apply them to a wide variety of different input data and also to produce a wide variety of different kinds of output data. And that's kind of really nice because you can focus a lot on building a scalable training system that you can then point at lots of different kinds of problems. And just to point out, these things have state-of-the-art results across a pretty wide range of different domains. Everything from speech and image recognition to, I guess we didn't put any NLP-related things, but there's a bunch of NLP-related benchmarks that sort of deep neural nets have state-of-the-art results on now as well. Okay, so a nice animated figure to illustrate the kinds of models we care about. Is it a cat or a dog? And one of the things that works extremely well today with deep neural nets is supervised learning. So if you have a big data set of labeled examples and you can take those input examples and run them through a deep neural net and then do some sort of classification task to predict the output label, then you can backpropagate results through that entire model and develop features hierarchically, automatically, without sort of having to sort of do a lot of hand engineering of anything in the middle of the model. You put in very raw forms of data, you get out sort of the desired output, and you can train it with backpropagation and SGD. So these models also deal really well with sequence data, in particular time-oriented things or sequence-oriented things like text, where you have a sequence of words or characters, speech and video. All these things are often dealt with very effectively with recurrent neural networks. In particular, LSTMs is something we've put a lot of emphasis on within Google across a wide variety of problems. And we've also found that you can use transfer learning across a pretty wide variety of tasks. You might have a very big labeled data set that's not exactly what you care about, and you can initialize your model that way and then have a fairly small supervised data set for some other problem domain you care about. And the pre-initialization actually gives you really good results even with a fairly small labeled data set. I think the whole community has discovered that it's very easy to get started using these techniques with like a single GPU card you can throw in your machine. And we think the nice property of it being applicable to so many different domains is that it's a nice common language across a bunch of different fields of research. You see people in everything from drug discovery and healthcare and computer vision and robotics, all collaborating on developing techniques that are effective for their problems that often are applicable to other kinds of domains as well. So we've developed over the past 4 years or so 2 different generations of big scalable distributed systems for doing machine learning, and in particular neural nets. The first one was the first system we developed, which was called Disbelief, and we published a paper about it in NIPS 2012. And that system was quite scalable. One of the papers we published about that used 16,000 cores to do unsupervised learning to produce pretty pictures of cats. So it was really good for production use and very scalable, but it tended not to be that flexible for research. If you wanted to do kind of a standard feed-forward neural net with up-down training of using SGD, it was pretty good. But if you wanted to do something more exotic, like reinforcement learning, or you wanted to have some sort of funky attention model in an LSTM, it wasn't really very flexible in expressing these kinds of things, because it was not quite as general. It was a little bit more purpose-built for the initial set of experiments. And as we got more experience, what we wanted to do was come up with a sort of a revision of that system that shared the good properties that the first system had, but was also much more flexible for research. And so that's how we came up with TensorFlow. We think it has the same properties of being scalable and good for production use that our first system had, but it's also very flexible and easy to express a wide variety of different research ideas. A lot of our researchers internally have been using it over the past year or so to express their problems. And we have a bunch of interns coming every summer, and they've been pretty happy expressing different kinds of exploratory research in it. It's also portable across a range of platforms, as you'll see. And we open sourced this about a month ago using a fairly flexible Apache 2.0 license. That sort of license basically means you can take it and do what you will with it. And we really hope to build up a vibrant community both within Google and outside of Google in sort of making improvements to the system and extending and improving it over time. So one of the things I'd like to point out to motivate why you want large, scalable, distributed systems, there's a lot of text on this slide. I just grabbed it from a paper called Scaling Recurrent Neural Network Language Models by Williams et al. It's been posted on arXiv, but there you can find similar kinds of examples in lots of different papers where people observe that both as you scale up the training data, which you see on the left, but you hold the model size fixed, generally you tend to get better results. In this case, it's measuring perplexity of a language model, so lower is better. And as you scale up the amount of training data you use, results generally get better. Similarly, on the right-hand side, you see that end state is the number of hidden units in an LSTM layer for the recurrent language model. You see that as you scale up the model size, you also get considerably better results. So both more data and bigger models tend to make things better. And if you combine those two things, you have more data and a bigger model, things will generally sort of get even better. But in order to do that, you actually need a lot of computation. And you really want a system where you can apply really big models to large data sets and get results quickly. That's kind of the main motivation for why we've been building scalable distributed training systems. So this combination of more data and big models works really well, but it poses interesting systems problems. In particular, because you need to throw so much computation at it, basically you can't just do this on a single device or a single GPU card. Once you get to a big enough data set, you get to the point where you're not willing to wait that long to get your answer. And so large-scale parallelism, often using distributed systems, is really the only way you can really do this. And then we also want to be able to easily express machine learning ideas and run them in a big, scalable, distributed way. OK, so let's look at a few different kinds of problems that we've tackled with deep learning at Google. And so we have some common language to discuss these things. And also, I'll point out that the general trend is towards sort of more complex kinds of models, things with lots of different kinds of embeddings for sparse data, generative models, layered LSTMs, things with attention or memory. All these things are add more computation, but also add kind of to the set of things you want to be able to easily express. OK, so one of the first problems that we worked on with our initial system was learning from unlabeled data. And in particular, we took 10 million single frames from YouTube and used a very deep autoencoding system to essentially learn to reconstruct those frames. And we used 1,000 machines, in this case, 16,000 cores. These weren't dedicated core machines, so we were sort of sharing them with a bunch of other work. And this model was actually quite large. It didn't have tied parameters in the convolutions or in the spatially localized neurons, so it had quite a lot of parameters. So it was quite challenging to train. But one of the things that happened was if you look at activations in the neurons in the top layer of that system, the system automatically learned very high-level features. So it basically learned the concept of a human face without ever being told what a human face was. And it also, it being YouTube, of course, learned what a cat was. If you look at the activations for another neuron. And if you then use that as pre-training and add supervision to the model, you see that you get neurons at the high level that respond strongly to very sort of high-level features, like is there a keyboard in the image, or is that a front view of a zebra, or is it some sort of waterfowl, things like that. The second main involvement we did, a collaboration, was working with the speech team to do deep acoustic modeling for the speech recognition system at Google. And this was one of the biggest models we trained at that point, was essentially taking acoustic data and then trying to map it to one of 14,000 triphones. And we had about 8 different layers in there. And these were fairly simple, fully connected networks with just a bunch of layers stacked on top of one another. The speech kinds of models that people want to express have been getting more complicated. So this is work by Tara Senath and others at Google on using convolutions, a bunch of deep LSTM layers, and a bunch of fully connected layers to essentially do the acoustic modeling for speech. And another trend that we've observed is that basically, sometimes when we go into the machine learning, try to use machine learning in different systems, at Google, we find that a team is already using machine learning in a few different places. And they initially just want to replace a machine learning model with a better one. But a more recent trend has been people are starting to think more holistically and try to figure out ways to take a whole subsystem that might have 3 or 4 different independently trained machine learning systems and then essentially replace that wholesale with a single end-to-end system that solves a more complex problem that sort of the 3 previous systems were collaborating to solve. The nice thing about that is systems with sort of 3 separate machine learning systems and some code to put them all together, you tend not to be able to optimize them jointly. Like that sort of manual, messy code that sort of stitches these things together, instead of it being a machine learned system all the way through. And what we found is that being able to use machine learning for an entire subsystem and just do end-to-end training makes the system both simpler to express and also perform better, because you don't have these artificial optimization barriers that crop up when you have separate systems. That's been true in speech. So there's been a bunch of interesting work done on end-to-end speech recognition where you go from acoustic waveforms to the output of the actual words. The end-to-end translation model that we'll describe later is another example of that. OK, and then another big important domain for deep neural nets has been convolutional neural nets for computer vision tasks. This all started with Alex Kruszewski, Ilya Sutskever, and Jeffrey Hinton's paper in NIPS 2012. This won the ImageNet challenge in 2012 with this sort of deep convolutional model with some fully connected layers on the top. And these models have been evolving over time. So in 2015, a bunch of Google researchers came up with a model that basically removed the fully connected layers and used way more convolutions and stacked them more deeply. And essentially, that's the model they came up with. And that model won the 2014 ImageNet challenge. And then more recently, like in the last few days, we've published an updated copy of an updated version of this model on arXiv that achieves a pretty significant drop in error rate. So if we look at the sort of progression of top 5 error rate in image recognition, a lot of this is due to more powerful models and applying more computation. And you also observe some things. So one is there's a big drop from the pre-neural net explosion to the year Alex Kruszewski's work won the ImageNet challenge. That was kind of eye-opening for the computer vision community that you could have that kind of significant drop in error rate. The next year, Matt Zeeler founded a company called Clarify. Matt was my summer intern before that. And he did a nice job winning the contest that year. And then the next year, you look at the 3rd, 2nd, and 1st place winners. They're all way below the winner from the previous year. And the Google Linnet inception architecture that I described was actually kind of interesting in that because it removed the fully connected layers, it had many fewer parameters than a lot of the other models. And I think that's an interesting trend that we've observed, especially when you're doing distributed training, because you're often shipping the full parameters of the network, of the model across the computer network. And having fewer parameters that you then reuse in many different computational operations is actually a better thing than having parameters that you only use sort of once, for example. We'll talk about that more in a minute. Andrei Karpathy, a grad student at Stanford, actually sort of simulated a machine learning algorithm on himself by giving himself a bunch of training data and then some test data. And he got about 5.1%. I don't know how many parameters he has, but it's a lot. And then the batch normalization method was introduced that sort of gives a nice significant drop in error rate. And then the Inception v3 that was just posted on arXiv a few days ago gives 3.46. An ensemble of those models gives 3.46 error in top 5. So we've gone from not even close to human to arguably as good or perhaps slightly better in some cases than human on image classification of 1,000 classes. The other point I'll make about models without many parameters is that a nice property that they have is they fit easily on mobile devices. So you can actually run the sort of more recent inception models quite effectively using 8-bit fixed point at multiple frames per second on a sort of high-end smartphone, which is kind of a nice property to have. A brief aside, we have some new news. The pre-trained Inception version 3 model we just released an hour ago, so you can download that and play with it. This message was just sent out to TensorFlow, discuss at tensorflow.org. But basically, there's a demo of how to use that for doing classification of images. Actually, we'll show something like that. There's Grace Hopper, and we think military uniform, which seems pretty accurate. There's a nice tutorial that's been written up on the website that shows you how to do that.
Right. So here, I'm just going to run a couple of images I took this morning. So for example, the example image, so here we have just a simple TensorFlow program that takes an image file in JPG and gives us the classification from ImageNet. So this, for example, is classified as military uniform with 81% probability, suit with 2%, and so on.
Maybe make the font a little bigger on the terminal.
So let's try something else. I'm sure you guys were in line this morning. So I have the crowd patiently staying in line. Let's see what ImageNet, what the CNN says. So this building is beautiful. This is unlike any other ImageNet picture, though. So it's a little tricky and out of domain. For those who work on image processing, they know what I'm talking about. And it actually says window shade with 41% probability, banister, church. So I guess
stained glass.
we are in a, it's
the glass
I guess
is stained.
It's believable.
It's a church of machine learning. Or something.
Right. Believe in it, please. Then a more prototypical example would be like a plant that is there outside. There's very nice plants here in this building. So this again is a pot, a flower pot with 49% probability. It says it's a window screen, which you could see why maybe perhaps it would say that. And solar.
It's Canada,
dish.
so it says hockey puck with
Right.
probability.
It's a very smart system. So again, like you can just download and play with this with your favorite pictures. I have one from this room actually. So let's do that tutorial room. So this is running on my machine locally. Of course, it can run on the phone or whatever.
And every time he runs it, it's loading up the parameters of the model. So
right.
It's
so
like not what you would do in a real system.
Not what you would do. So here it says folding chair, 42%, stage, 38%. Again, this is perhaps not the most prototypical image you would see in ImageNet. It says cinema, water bottle. I guess it's zoomed in.
See?
Yeah, it's impressive. That pixel over there. Well, these things are getting better every day. So anyways, try it. We just released the parameters, and later on we'll also release the training script.
Yeah.
Not in this release, though, but this will also be released for you to train or fine-tune this model on whatever data set you might want. And
Okay.
that's it.
All right. So the question we kind of asked ourselves after we had been using disbelief for a little while was, what do we really want in a research system? We realized that there were a lot of research ideas people wanted to express that were not as easy to express in the first system as we might have liked. So you really want that ease of expression where I think you'll see in some of the demos that we're going to show you of how you express, say, very deep LSTMs, maybe with attention models. You really want that kind of thing to be, a matter of an hour of work, not some like heroic multi-day effort in C++ with void star pointers flowing around and so on. And then you want all the other properties that our first system had. You want the scalability so that those experiments can run quickly. Portability is really nice so that when you get a good research idea and you want to move it into a production system, you can use the same system to go from that expression of the research idea to running it on your mobile phone or running it on a big distributed data center for production inference. The other thing that's kind of nice is you want reproducibility. So if people start sharing the expression of these research ideas, you want people to be able to take code that demonstrates the research idea and reproduce those results, and so on, and production ready, I sort of touched on. So that's sort of why we developed TensorFlow. And we also decided that it would be nice to open source it so that we have a way of sharing the research we've done internally with the outside world. And so the outside world can also use this to express research ideas and get those same benefits that we're getting. So the thing that we open sourced initially was a single machine version of this, but updates for the distributed implementation are coming soon. And there's a website there with nice, pretty pictures and a lot of pretty good tutorials. I think one of the things that people have liked about the initial open source release has been that it's quite well documented, I think. And it has a bunch of nice tutorials that show you how to use the system for a variety of different kinds of researchy problems, and also very simple kind of things just to demonstrate the mechanisms underlying this. So as I said, the motivations were sometimes when you've been using a system for a while, you can take a step back as you're rethinking what you want to do as you revise it, or maybe write a slightly different version of a system, and really have a better understanding of the way it's been used in practice and the kinds of things that were difficult and the kinds of things that it did well, and preserve those and improve on the things that it didn't do so well. Let me give you a brief overview of kind of the architecture of TensorFlow, and then we'll show some simple examples, and then we'll move on to more complicated ones. So the core TensorFlow system is basically this graph execution engine that is in C++. It supports a wide variety of devices, and that set of devices is extensible. So it supports CPUs and GPUs in the open source release. If people start developing kind of funkier hardware devices, it's pretty easy to plug in a new implementation of a device abstraction and have that be something that the system supports. It also supports a wide variety of different platforms. So it runs on Linux, it runs on Android. We have an internal version that's running on iOS that we intend to release as soon as we kind of polish a few rough edges of it. And then we have different front ends that are the way you specify a graph, specify the kind of model you're trying to do and how you want to use that model. So right now we have Python and C++ front ends, and by open sourcing it, we hope the community and perhaps other people at Google will release other kinds of front ends that allow you to express machine learning models that ultimately generate a TensorFlow graph in other languages. So we expect probably a Go front end. Several people have expressed interest in that. Maybe Java, JavaScript. There's a bunch of TensorFlow issues on the GitHub repository that show the kinds of languages people are interested in. And we hope the communities will sort of work on adding new front ends. So as I said, the system's portable. The thing that we open sourced initially is these first two, and the next thing coming will be the distributed version in the open source release. The reason we didn't open source the distributed version initially is our distributed implementation is a little tied to our cluster scheduling system and other things that aren't open source, but we're going to we're developing a open sourceable system that uses Kubernetes to do the distribution, and gRPC for open source RPC mechanism. So the basic computation in TensorFlow is a data flow graph where the nodes do different kinds of operations, and then the data that flows along the edges are arbitrary tensors of some primitive type and arbitrary dimensionality and shape. So for example, a two-dimensional floating point tensor is a matrix. The other thing that is different than some data flow systems is that the graph has the ability to maintain state. So we have these things called variables, and then we have some operations that can operate on variables to update them, to update their state. So most of the graph is a stateless computation, but the way that you kind of express machine learning ideas is you often have the parameters of the model in variables, and then you do some computation to compute how you want to update those parameters. And then you update them with one of these updatable operations. As I said, we support different devices. So one of the one of the tasks of the TensorFlow implementation is to take this arbitrary graph and to map it onto the set of devices you have available in your system. So in particular, device A here might be a GPU, and device B might be a CPU. And you want to have the graph expressed in such a way that then the system takes care of mapping these computational operations onto different devices. And not every device is necessarily going to support every kind of operation, so the system needs to take that into account. And it wants to do so in a way that it's the most efficient way possible. So like it'd rather use a GPU for big matrix multiplies than use a CPU, for example. The way that we implement the distribution and different devices, even within a single machine, is that whenever an edge crosses a boundary between devices, so we've got a source node that's on one device and a destination node that's on another device, the system then rewrites the graph to have a send and receive node pair on that edge. And that send node essentially is going to capture the tensor that's coming out of that biases variable there. And the receive node is going to set up a communication channel and receive the tensor when it's available on the other device. And so by encapsulating, and so this happens for all the devices that cross these edge boundaries. And so that graph transformation happens under the covers in the TensorFlow implementation. One of the really nice properties of doing this way is that the send and receive node implementations effectively encapsulate all the different data transfer in the system. So if you have, for example, 2 GPU cards on the same machine, the send and receive node implementations might do a local GPU to GPU copy. If you have a CPU on different machines, 2 CPUs on different machines, you would end up using a cross-machine RPC. If you had GPU cards on different machines and they support RDMA, transfer across the network, the send and receive node implementations would use RDMA to transfer that data. Whatever makes the most sense and is the most efficient for transferring that kind of data. And it kind of means that all the complexity of transferring data in the system is encapsulated just inside the send and receive nodes, and the rest of the system kind of doesn't really need to deal with it. The system's also extensible, so the core system defines a bunch of standard operations, things like matrix multiply or element-wise add, or do a JPEG decoding of this image and compute me the actual decoded two-dimensional or three-dimensional image. And then kernels are device-specific implementations of operations. So pretty much every operation is implemented on CPU, and then we have a bunch of kinds of numeric operations that also have GPU implementations, for example. And it's very easy to add a new operation and then define a kernel on either just CPU code or just GPU code or on all of the above. If you define it on all of the above, then the system has more flexibility when it decides where to place that node. It could place it on a CPU or a GPU if it has kernel implementations for both. And that's sort of designed so that people can extend it with new functionality and have that map directly into sort of just new graph nodes showing up. Then the main other interface in TensorFlow is a session interface. So the client program describes the computation graph that it wants to operate on using a series of extend calls that add nodes to a computation graph. And that starts out empty. So you can think of, usually you start out with an empty graph and you make one extend call, and now you have a computation graph. And then you want to be able to run little bits of that computation graph. And the run call doesn't necessarily have to execute the whole graph. It can execute an arbitrary subgraph, as we'll see in a minute. Optionally feeding in tensor input and retrieving tensor output. So you can kind of run part of the model, get some of the results that it's computed, look at them, inspect them, decide what to do next, feed that back into the model if you want, or you can have your entire model graph just do all the computation you want. But being able to poke inside is very useful for debugging or other kinds of sort of inspection. Typically what you're going to be doing is setting up a graph with one or a few extend calls, and then you're going to be running little pieces of it, either the same piece or maybe a few different kinds of sub-pieces of it, thousands or millions of times when you're training a deep neural net. This is kind of nice from an optimization perspective because it means the system can do a bunch of work on the graph at extend time and amortize that optimization work over lots and lots of run calls, and also set things up so that run can be efficient and extend can be relatively not slow, but can be more contemplative about the graph. So the two different configurations that we support are a single process configuration. This is sort of what's in the open source release today, where you have a client program that's calling through the session interface to extend the graph and then to run bits of the graph. And then there's a master sort of component. In this case, it's not a separate process or anything. It's just sort of another bit of code that's running. And that master has a bunch of devices that it knows about. You know, if your machine has, say, 8 GPU cards and a CPU, then it'll have 9 different devices. And those devices will be told to execute little bits of the subgraph by the master. Now, in a distributed setting, it looks pretty much the same, except the pieces have been separated into separate processes that potentially are running on separate machines. And so the client process will make RPCs to the master to do extend calls and to do run calls. And then the master may have a bunch of different workers, which each have their own devices. And it'll partition the graph that's been given to it across these different devices as it makes placement decisions about which devices are going to be executing which nodes in the graph. And so it basically can then map that down to a subgraph that each worker process is responsible for with send and receive nodes between all the devices in the system. And then it does RPCs to the, when the client says, please run this graph, the master process will go ahead and do run calls, RPCs, to say, please start executing this subgraph that you own. OK, so remember I said that when you do a run call, you can execute an arbitrary subgraph of the graph that you've described. So here's a graph, a full graph that's been described. And now the user makes a run call where they say, gee, I'd like to just pretend like I'd produce this output from the B node. And I'd like to run the graph in such a way that I can compute the output from node F. So in that case, what's going to happen is we're going to rewrite the graph. And we're going to figure out, we're going to insert this special feed node, which is going to accept the data from the client that it wants to put in place of the output of the B node. And then we're going to say, OK, we want to run and compute the output of node F. So what is the transitive dependency of all the things we need to run in order to compute the output of node F? Well, that's nodes C and A, right? We don't need to run D and E because they don't contribute anything to the output of node F. So by doing this, you can essentially have a little subgraph that you're going to execute, even though you've described a more complex configuration of things. We often do this so that we actually have a few different conceptual graphs, maybe one for actually running the model computation, maybe one that you can say, I just want to run up to here, and that just does inference in your model, but not training. Another bit that might sort of aggregate a bunch of save operations, and you can say, I want to run this node. When I run this node, it's going to save the model to disk. So these little subgraph things we think are pretty handy. OK, so let's switch and give you a couple brief examples of fairly simple things in TensorFlow, and then we'll switch back and describe more complicated things.
Cool. So let's actually look at how code looks when I run. So I'm running here locally using the open source version that anyone can use. And I'm going to first show a very simple computation graph that computes the power method to compute an eigenvector. So this is a very simple conceptual exercise which takes matrices or tensors. And here, the basic algorithm is that I'm gonna be given a matrix, and I'm gonna multiply this matrix by a vector many times. And this is proved to converge to the largest eigenvalue eigenvector, assuming that the eigenvalues exist and so on. So as I said, this is just for convenience on showing essentially the running this. So let me show the menu. maybe I'll show the toolbar. Where is it? All right. So I'm just going to do a bunch of imports first, and then let's go over this. So I'm logging some stuff, including the graph definition, actually, so we can take a look at it in a second. So I'm going to remove that directory here first. And then I'm going to declare a session. This is an interactive session, but usually you would have a normal session with an empty graph initially. And I'll have two special nodes that I'm defining. Here it's W, which is a placeholder. Placeholders means I need to feed data to them whenever I want to run the graph, if the output I'm requesting is on the critical path of W. And this node is actually the matrix I'm going to compute the eigenvectors on. So I'm just naming this node. I'm saying it's a float32, and I'm saying it's an n by n tensor or n by n matrix. And then x is just simply going to be a variable that's randomly initialized, and it's n by 1. And this variable is actually, since it doesn't matter, any random vector will do. I just don't set it to anything in particular. So TensorFlow will just choose some random values, typically from a random uniform or Gaussian. And then the computation graph, what I'm going to do is I'm going to have a for loop. In this case, I'm doing 20 iterations here, where I multiply iteratively W times X. I'm getting the result as X, and I keep doing this over and over for 20 times. And then my last the result will actually be, I'm just going to normalize this X vector. So I'm just going to essentially divide X by the square root of the sum of X squared. That's simply to make sure that I get a result similar to what NumPy would give me when I compare what TensorFlow computes with the ground truth. Then I'm creating a summary writer. That's useful just for us now to visualize the graph to see what exactly goes under the covers there. And in this section, I'm just running the graph. So I have a W, the NumPy version. So you typically use NumPy to feed data to TensorFlow. You can do other formats, but this is the most standard one. So I'm going to just simply create a matrix and ensure that it's positive, semi-definite, and it has an eigenvalue that is large enough so that this method actually works. And after defining this matrix, I'm just initializing all the variables. Here, the variables are simply this vector that doesn't matter what it is. So I'm running this initialization code. And then I'm just simply going to print the result. So I'm fetching here the result, as Jeff was saying. This will take care of what needs to be run and what doesn't need to be run. And this second argument here is that W that you need to feed, I'm going to set to this NumPy array. So I want to feed this. Then I do a little bit of shaping and to make sure that displaying will be readable for us. And so I'm printing this vector, the eigenvector. And then I'm also printing just from linalg the actual eigenvector of the largest eigenvector of W.
That's not a TensorFlow computation.
That's just, yeah.
A comparison, point of reference.
Right. So let's run this. And this run, note that this, so the results from TensorFlow and NumPy are the same up to a -1 constant just because it's the same eigenvector regardless of positive or negative. And so this basically computed the graph. I can run this again, and you'll get slightly different values, but essentially they match. So the algorithm works, no surprises there. And let's also take a look at how the graph looks like. So here I have TensorBoard, which is our tool for showing the graphs. Yes. I'm going to make this somewhat smaller, and I can zoom in. So here, there is the graph of computation, and it's very useful as a researcher once you've developed the model to actually look at how it looks. Maybe you made a mistake or you don't quite understand the flow of computation. So let's look here what's going on. We have this W that, remember, this is going to be provided by the user whenever we run. And then we multiply by X, which is just a random vector. And here we have this thing that actually collapsed. So let's uncollapse these nodes in the graph, and we'll see very clearly what the algorithm actually does. So essentially, no surprises again. We take W into this block, and then the result of w times x. And then we just iteratively multiply by w over and over again for 20 time steps. So that for loop in Python became part of the graph, an unrolled version of this matmul for 20 time steps. And then if you recall, at the end, I'm just normalizing the result, so to make sure that visualizing it makes it's an normalized vector as NumPy returns that. And so the result, I'm just simply here multiplying it by himself, then summing, taking the square root, and then the result is dividing the same vector divided by the norm of the vector, essentially. And this result thing is the thing that I'm putting out here.
So go back to that just for a second.
Yep.
So when we ask to run up to result, we're going to compute in this graph the transitive dependence of all the things we need to run in order to compute the output of the result node. And that's basically that entire graph.
Mm-hmm.
So when we run the computation, it's going to essentially run all those things. And if those things had happened to be mapped onto different devices or whatever, it would sort of transparently do the send and receive nodes and eventually get the result output and give that back to the client.
Right. So this is the first example. Hopefully that's clear. So
Yeah,
we
kind of described
a little
that.
bit. Yeah.
There's some memory management for tensors going on under the covers so that we delete a tensor's memory when it's no longer needed. Yeah, that's pretty much.
So let's look at now the simplest and probably not very smart neural network you've ever trained. So here, obviously, we use TensorFlow to compute derivatives or optimize cost functions. That's really what we are up for. So in the next example, I'm gonna minimize a function that's very simple, which is x transpose times w times x. So it's a quadratic form. And of course, trivially, this has a minimum of 0 if w, again, is positive semi-definite. And I'm going to show in the graph, actually, how the gradient actually is what we expect it to be for this example, which is 2 times wx. So let's look at the code here for a second again. So same thing, we create a session. In this case, we are going to actually run this in a slightly different way, but not too different. So we have w, which is the matrix, again, expected to be fed every time we call run, that we run the computation. And x, similarly, is also fed every time step. So x is the x over there. Okay, so this is a matrix n by n and a vector n by 1. And then we're going to compute this f of x in TensorFlow. So we will keep around the version of the transpose of x, xt, so tf transpose. All the operations, I mean, there's a lot of documentation of all sorts of operations that we might want to do on tensors. And the actual f is just going to simply be multiplying w times x and multiplying the result on the left by x transpose. So very simple thing to do. We can actually, so this is where the magic starts to come in. So you can define a forward algorithm. This is extremely simple, but this can be very complicated, as we'll see later on. And then we can say, okay, now please give me the derivatives of this f, which is a scalar, if you did the math correctly, with respect to x. X is the thing I want to optimize. So I want to find the x that minimizes that function. And this grad is going to be a list of tensors that are equal to the gradient of f with respect to x. So that's great. And further, you can, since this is symbolic differentiation, you could also implement a second order method, which makes a lot of sense when it's a quadratic, because Newton method gives you the optimal in a single step. And this would simply be, well, the Hessian matrix would be the gradient of the gradients with respect to x, for example. We didn't do this here, so the graph doesn't look too messy, but you get the idea. Similarly here, we will write out the graph to disk. And we initialize similarly like the W, the NumPy version of these tensors, and the X. The X, we initialize it with all ones. This is a convex problem, so it will not matter what we initialize it with. And then here, I did my own gradient descent version, because this is a very simple problem. So I have 50 iterations where I call this run. And here, in this run call, is somewhat more complicated, just because I want to retrieve the actual value of f. So here is a list. First, I'm going to retrieve f, and then I'm going to retrieve the gradients, which I'm going to apply externally, just because I can. And then, of course, I need to provide, remember, there's these two placeholders. I'm going to provide W and X to the graph every time I run this step of computing the gradient of F with respect to X. So after that, I'm going to update my X externally in NumPy. You can do this, of course, also as part of the graph, but in here, I just put it externally. So I'm going to update X by subtracting a learning rate 0.1 times the gradient. And then I'm going to also create a summary of how I am doing in terms of objective function as I iterate over this very simple, silly example of 50 time steps. And I'm going to add this to the summary. And I'm just also going to print F, and you will see, hopefully, how this works. So let's play this cell. And here, initially, you see the value for F is sort of 19, so it's pretty bad. And then it converges down to 0, like, eventually, right? This is a first-order method. The point is not to get to 0 very fast. It's just to show how it works. So let's take a look at, actually, a tensor board for this particular graph. So let me refresh this. I'm running this locally, as you can see. First of all, the events. So not surprisingly, we see here actually, well, I've run these many times, but like there's the curve that it started somewhere at around 20, and it converts to 0 after 50 time steps. And more interestingly, let's look at this graph. So first of all, we understand the forward graph. We did something similar before. So we take Wx, and we have here X transpose, and we just compute W times X and multiply by X transpose on the left there. So this is the forward graph. We have an example of this. Let's look at, perhaps more interestingly, what this gradients magic Python sugar that we have did to our graph. So if I expand this gradients tab, and assuming I can minimize this so I have some space. So this is what the gradients or the backward pass for this very simple optimization problem looks like. So here we have, first, we take the shape of the loss, and we fill it with a constant of 1s. So this is simply 1, the vector constant 1. And then the first thing we do here is actually computing 1 times Wx on the left-hand side and 1 times X transpose on the right-hand side. Okay? So on the left, we have Wx. On the right, we have X transpose. Let's follow the left path, for example. So here, after we compute Wx, we just kind of compute the gradient with respect to transposing, which is just transposing. So this is the left branch, so to speak, through this path here, before we add, is going to be equal to Wx, or X transpose W, depends on the shapes. Okay? And then on the right-hand side, we have so far X transpose times 1. Remember the thing from the bottom here, this is just 1s. And then if we expand this Wx grad, we see, as Jeff was saying, this graph has extra nodes that will actually not be run. So here there's a matrix multiplication of X transpose times X, which will not be run because we don't request the gradient with respect to W. And on the other branch, we're multiplying X transpose times W. And so this branch is actually the one that flows up to the gradients. And what we are adding here at the top is X transpose times W plus, again, X transpose times W. So the gradients is 2 times X transpose times W, and there's no surprises. Obviously, we don't need to check this every time we run this graph, but it is good to see that our intuition and the math here works out. But in general, for a neural network, we just trust, and of course there are a lot of checks and so on, that these gradients will be correct. So now we have this very cool thing where we literally write equations and we say, hey, take the derivative of this with respect to that, and then we can just update parameters and so on.
I'll point out that this is kind of the unoptimized graph that the Python code generated to give to the execution engine. Underneath the covers, the execution engine actually is doing some amount of optimizations, and we expect to increase that set of optimizations over time. So initially, it's doing, for example, common subexpression elimination. So it's going to fold those two computations of the two matrix multiplies with the same inputs into probably one computation.
Right.
Okay. So one of the things that happened after we open sourced TensorFlow is people started doing performance measurements of it, and that's great. We were really excited that people are sort of excited enough to measure it. And our single device performance didn't look that great initially. Turns out that so this is some measurements done by Sumit Chintila. He has a nice set of open source ConvNet benchmarks for a variety of different models. I'm just showing AlexNet here, but the other results were kind of similar, where he's measuring AlexNet, the set of kernels involved in AlexNet, on a bunch of different implementations of those kernels. So one is, for example, the third line is cuDNN version 2, which cuDNN is an NVIDIA library that does convolutions. And that is showing cuDNN v2 driven by torch code. And that got about 70 milliseconds and 231 milliseconds for a full forward and backward pass. And our initial performance was significantly lower than torch using the same cuDNN. Obviously, cuDNN v3 is significantly faster than cuDNN v2. But ultimately, these things are sort of using the same code underneath the covers. So there's two main factors of overhead why the initial TensorFlow numbers on a single device don't look that good. One is, turns out we use an internal gcuda-cc compiler for compiling our GPU code. And one of the things we wanted in TensorFlow is to have the ability to have tensors with more than 2 billion elements. So we use 64-bit indexing in all of our tensor indexing operations. And it turns out NVCC, which is used in the open source release when you compile 64-bit tensor indices, it's kind of an obscure thing, but the code was roughly 20% slower for some kinds of operations. If you're doing a lot of tensor operations, if tensor indexing is slow, that's not a good thing. And the second thing is the versions of convolutional libraries being used. So we're working on upgrading to use the sort of more modern cuDNN v3 and maybe cuDNN v4 that's coming out soon. We think that'll help a lot. But for the moment, we've been focused on looking at the other sources of overhead and getting things more reasonable in that respect. So the first thing we wanted to do is, since Sumit has a slightly different machine than we had, it's the same GPU card, but we have a slightly different CPU, and it's like a slightly different kind of workstation. We wanted to make sure we could reproduce the results that Sumit showed. So TensorFlow 0.5 is the initial version. And we pretty much basically could match his results modulo a few, basically the same results. And then we've been working hard on improving the performance of the initial TensorFlow release to fix some of these NVCC compilation issues and a few other kinds of sources of overhead. And we're about to release TensorFlow 0.6 in the next probably week or so. And what you'll see is that we've improved things considerably, especially when you compare the same underlying cuDNN library. So we're basically significantly better, more than 30% better from the initial release in about less than a month. And we're basically on par now with the torch implementation for cuDNN v2. And these are the measurements we've made of the code we're going to release soon on the same machine that Sumit does, but it's not an independent assessment. But basically, you see the results and performance improvements hold across a bunch of different of the convolutional benchmarks. So we're reasonably happy with the progress here. We will continue to work on this. The second prong for making things faster is just to upgrade to the faster core libraries like cuDNN v3. That work, unfortunately, isn't going to make it into the 0.6 release, but will follow on pretty soon after that. So we hear the community. We're working on it. We think we'll be a lot better pretty soon. The other thing I'd like to make is the reason we kind of haven't focused on single device performance is we've focused a lot on the distributed implementation. And the reason for that is single device performance improvements give you like 30% improvements, and that kind of is a cap on how much better things can get if you're using a single device. But being able to take a system and scale to, say, 40 GPU cards or something is the kind of thing that gives you 30x improvement. And so we focused a lot more on the distributed implementation because that is the thing that really makes your research and your models train more quickly. So let's switch gears a bit and really say why we care so much about scalable, distributed, and parallel implementations. And that's because if you look at the time it takes from you to express a research idea and then turn around an experiment where you now know how well did that idea work, what are the next sets of things that I want to do, if that time is in kind of minutes or hours, that's really, really magical because it's really more like interactive research. I can express something, try it, get a quick sense of whether it's working, figure out what I'm going to do next. A little bit worse is 1 to 4 days, and that's kind of the tolerable range that most of our training regimens tend to be in, is that you come up with an idea, you launch some experiments, maybe you launch several experiments in parallel because you're now in the 1 to 4 days kind of regime rather than minutes or hours. But essentially, that's a pretty good spot to be in. If you're kind of at the other end of the spectrum where a single experiment takes more than a week or more than a month, that's a really hard situation to really make productive iterative research happen. So that's really what we think the benefits of having these really scalable and distributed implementations of neural net training in particular, because that's a very computationally intensive task. That's really why we focus a lot on the scalable and using lots of devices to bring this experiment turnaround time. We're even happy to throw more resources at it and get sublinear speed up as long as the speed up is still pretty significant because of the feel that it has in terms of how it changes how you do research when it's much more interactive. Okay, so now we're going to talk about some techniques for expressing things in parallel, and then talk about how you can express some of those ideas in TensorFlow relatively easily. So the absolute best way to increase the speed at which you can train a model is to decrease the step time. I'm ignoring other kinds of algorithmic issues like maybe second order methods would be useful. But let's say we're using a first order method like stochastic gradient descent and we're trying to train a big neural net. The best way possible to decrease the training time is to decrease the step time. And lots of these models have huge amounts of inherent parallelism in the kinds of computations they're expressing. And the real problem you have when trying to parallelize execution of a model is distributing the work in such a way that communication doesn't kill you. It's very efficient to do lots of computations on a single device or a single CPU core, but it's not so efficient when you start to communicate across CPU core boundaries or GPU boundaries and so on. So you can kind of influence that a bit by coming up with model architectures that are not just giant fully connected layers, for example. Like local connectivity, the original AlexNet actually had 2 towers of convolutions that had relatively infrequent communication between the 2 towers. And that's the kind of thing you can do when you want to parallelize across multiple devices to minimize the communication cost killing you. Yeah, so there's lots of ways of exploiting model parallelism. So on a single core, most modern machines these days have vector-based instructions which can compute results of 4 or 8 sort of vectors at a time. So those are really useful and very, very easy to exploit. You just usually you just give a funny compiler flag to your compiler and off you go. Or you have a precompiled kubeless library or BLAST library that does that. Doing this across cores, you can use thread parallelism, which is pretty cheap. And you can essentially partition large sort of matrix multiplies or something across 8 threads and do bits of those computations across the different cores. If you have multiple sockets, then inter-socket bandwidth can kind of be an issue. Across devices, when you're communicating, your bandwidth to GPU memory on that same card is typically 200 or 300 gigabytes a second. When you're going off GPU card to another card on the same machine, on the same PCI bus, you're now more like 6 or 8 or 10 gigabytes per second. So there's like factors of 30 drop-off in communication efficiency there. That starts to be felt pretty quickly. And across machines, typically it's even worse, where you're limited by whatever network speed your machines are connected with. So it might be 10 gigabits per second, sorry, or 40 gigabits per second. 100 gigabit networks are sort of coming soon, but are pretty expensive. So you're already lower in communication bandwidth across machine boundaries than you are even across devices. So it's really important to sort of figure out how you can make effective use of all the computational capacity you have, perhaps on lots of GPU cards and lots of machines, in such a way that you don't spend all your time waiting for the network. So let's just illustrate model parallelism here. We have some deep convolutional neural net, and we have neurons that have localized connections. So typically, each neuron takes as input some small patch of data from the layer below it, not the entire set of data. And we can partition this model pretty effectively. We can essentially slice it into 3 different pieces and run those on 3 different devices or 3 different machines. And the nice property that has is that because these neurons have local connections and we've sliced the model vertically, then the communication you need for the activations of the neurons is actually mostly local to that device. So mostly all the communication stays within the device, and it's only neurons whose input comes from basically pieces of the network that have been split. So if you look at the second neuron from the left here, that one has to communicate across device boundaries, across partition boundaries, to get the data it needs in order to compute the activation of that neuron in partition 1. But most of the other ones are local. So model parallelism is a really great and effective way to parallelize things, and it can really effectively reduce the step time, and that's sort of the most effective way of getting parallel training, getting your training to happen more quickly. The other approach that's complementary to model parallelism is data parallelism, where essentially you're going to use multiple model replicas, and they're going to collaborate to process different examples at the same time, and they're going to collaborate to update the parameters in the model in some sort of shared way. The speedups depend pretty highly on the kind of model. So if you have dense models like convolutional neural nets or LSTMs, you can often get between 10 and 40x speedup from 50 replicas. For our image models, we typically see 40x speedup for 50 replicas, which is a pretty satisfying return, because getting your results 40 times faster is a really, really nice property. For sparse models, often we have models that have these very large embedding layers. So you're mapping from, say, a vocabulary of 100 million unique words into, for each word, a 100-dimensional vector. Most examples don't touch but a few entries in that large embedding matrix. And so there you can use even more replicas. We often train with 1,000 replicas, or sometimes even more for some of these very sparse models, because the gradients don't interact very much in those cases. They're only updating little teeny bits of these giant embedding matrices. OK, so data parallelism is this notion where we're going to have this set of centralized parameter servers that are going to have the state of the model, and we're going to have many replicas of the model that are going to read data from some input format on disk. And before every one of these replicas does an operation, it's going to get the current state of the model parameters. That's P. It's going to compute some part of the graph, execute some part of the model to compute the gradient that it wants to apply to these parameters. So that's delta P. And then it's going to, instead of applying it locally, send it back to this centralized parameter service. And that centralized parameter service is going to apply that update. And before the next sort of mini batch, it's going to essentially do the same thing. P prime, delta P prime, and P double prime is now computed from P prime and delta P. And you can do this asynchronously or synchronously, but you can essentially have all these model replicas processing different input examples and all updating the parameters simultaneously. So the two main choices you need to make are, do you want to have, if you have 100 replicas, do you want to have them synchronously operating in lockstep, so that essentially at the beginning of that step, all 100 replicas get the same set of parameters. They each read a different set of examples from disk. And then essentially you combine the gradients in some way before you apply them to update the parameters. So then you essentially have n replicas that are really just parallelizing across a batch of examples. And so now your batch is sort of n times larger. And for most problems, for large data sets, you can generally have a somewhat larger batch size. And so that sort of works OK for like up to 10 to 100 kinds of sizes. You can also do this asynchronously, where now every replica is operating independently and grabs the parameters at kind of a random time, not synchronized with any of the other replicas, and then computes a gradient. Now, the drawback of this is, well, one nice property of this is that it's relatively fault tolerant. So if one of those replicas dies, all the other ones just continue processing. You're not waiting in lockstep for all 100 replicas to do something. But the drawback here is that now you're not synchronized when you apply the gradient updates. And in particular, when you apply a gradient update, other replicas may have also applied gradient updates to the parameters, and parameters may have moved. So you're now applying gradients to a point in the parameter space where that gradient doesn't necessarily apply. But it turns out this sort of works OK, because most gradients either point in the same direction or it just adds a bit of noise to the system, and that's sort of OK for most problems. We've discovered that, depending on the problem, 10 to 1,000 replicas work just fine in this regime. You can also do something hybrid where you have m asynchronous groups of n synchronous replicas, and that's sort of like a somewhat bigger batch and then asynchrony on top of that. So one of the big considerations here, remember I said that one of the nice trends in the image models was that essentially, at least the inception models tended to have many fewer parameters than some of the other models that tended to have big fully connected layers. In particular, because we're communicating the sets of parameters of the model across the network fairly frequently, basically every mini batch, we really want models to have not too many parameters in order to save our precious network bandwidth. So by using a mini batch of size b, you're effectively going to read a floating point number across the network. And a mini batch of size b, you'll typically reuse that floating point number b times, right? If it's sort of a typical fully connected layer. You're now going to do matrix multiplies and reuse that parameter b times. But certain model structures have additional nice properties where they reuse every parameter many times within each example. So within the same example, a convolutional model, for example, tends to take the same set of parameters and apply them at many different spatial positions within the model. So you might download 100 kilobytes of convolutional model parameters and do 100 million floating point operations using those 100 kilobytes worth of floating point parameters. Recurrent models also have the same property because you tend to unroll training in time, where you unroll the network 10 to 100 steps. You're now going to reuse the dense parameters in the recurrent layer t time steps during each training step. And so that's another nice property where you're now bringing not as much data across the network, doing a lot of computation. Remember, the benefit you have in a big distributed system with lots of, say, CPUs or GPU cards is you have tons and tons of flops, essentially floating point multiplies you can do every second. And the thing that will slow you down is if you spend most of your time waiting for data to come across the network. So data parallelism is basically one of the key things we use to train virtually all of our models at Google. So we recently launched a system in collaboration with our search ranking team that uses deep neural nets for some aspects of search ranking. And that system uses 500 different replicas to train that model. It's obviously got a lot of training data and a pretty expensive model, and using lots of replicas allows us to train this model in a reasonable amount of time and to iterate on what kind of model structure should we be trying. The training of our inception model uses 50 GPUs. We typically get maybe a little bit less than 40, maybe 38 to 40x speed up on that. We recently launched a system called Smart Reply that Oriol will talk about in a minute. That uses 16 replicas, each of which has multiple GPUs. We've been doing some language modeling work on this 1 billion word public data set. We have a language model that uses both data and model parallelism that Oriol, of the kind that Oriol will describe in a minute, and that uses 32 GPUs to train. that model. So data parallelism is a really, really effective technique and one we think really gets you to the point where your research happens in hours or a day, not many weeks. So here's kind of a typical training graph. This is for training an inception model using synchronous training. And it's comparing the time to accuracy. Hours go along the bottom, and accuracy, top one accuracy goes along the y-axis. And it's comparing 10 synchronous replicas with 50 synchronous replicas. So essentially, we're using a batch 5 times as large in the 50 replica case versus the 10 replica case. And although these graphs can be kind of deceiving, like they look like, oh, they're not that far apart, right? But actually, if you look pretty closely, they're actually 4 times faster when you use 50 replicas instead of 10. So we've thrown 5 times as many resources into the problem, and we get 4 times the speed up, which is a really nice property. This is kind of the typical training graphs you'll see in these data parallel distributed systems. OK, so now how can we express these kinds of concepts using TensorFlow? That's one of the things we want to do, is to make it easy to express these kinds of parallelism, or ideally maybe to have the system figure out all these kinds of parallelism underneath the covers. And we'd like to do so with very minimal changes to kind of the straightforward single device model. So one of the things that TensorFlow needs to be able to do is, given a graph and a set of devices, it needs to decide which device is going to execute, which device is going to execute each node in this graph. And one of the things we allow users to do, because our heuristics are not necessarily perfect, is we allow users to specify both full and partial device constraints. You think of these as hints about where in the distributed system you want this kind of this particular node's computation to execute. Devices in our system are named kind of hierarchically. So we have a job name, a task number within a job, and then each one of those tasks you can think of as a process. And each process is responsible for perhaps many different devices if each machine has multiple GPU cards. So you might say localhost CPU 0, or you might say worker task 17 GPU 3. And you can also specify only some of these constraints. So you can say device GPU star, meaning I have to have this node on some GPU. I don't care which one. Yeah. So those kinds of things are fairly easy to express. And then we have a node placement algorithm that's going to take these hints, which you may have left completely blank, so we may not have any hints. And it also has a cost model of the graph. So it has estimates or measurements of the node execution time. And it also has estimates or measurements of the tensor sizes that are flowing around along edges in this graph. And that allows it to, that data is sort of the input to the placement decision, and then it's going to make placement decisions. We currently have a relatively simple greedy algorithm described in the TensorFlow white paper, but this is an active area of work. We think this actually we think placement could be done with some sort of reinforcement learning algorithm using a neural net, which would be very meta. But OK, so you're going to show the CFAR. Oops, sorry.
Right, so here I'm just going to show how things look like for when we do
2 GPU training.
2 GPU training. So I'm going to color the graph, not by structure, but by device. And then you'll see something that's fairly common when you use a convolutional neural network, or in this case, 2 convolutional neural networks that are computing a forward and a backward pass on a bunch of images of batch size, let's say 32, to aggregate them onto a single batch of 64 images. And so here you'll see there's 2 towers, tower 0 and tower 1. Each of these towers are in different GPUs. So there's a GPU 0 and a GPU 1. This is, by the way, part of the open source. So if you have 2 GPU cards, you can just run this plan and see how it looks like and how it scales well with a number of GPUs in this case. And then so each of these towers, of course, like let's expand this for a second. Each of these towers is, some convolutional neural network with many like nonlinearities and convolutional and fully connected layers and so on. This is for CFAR 10. And if we expand this minus again, so again, this will do a forward-backward pass on the two towers on the two different GPUs. And then all the parameters actually are on the CPU, so that we don't, both of the towers need to retrieve parameters from somewhere. So we decided in this case, we will put the parameters on the CPU 0 in this case. And so all these global step, conv1, conv2, local 3, all these are parameters stored in the CPU. And again, these are all going to fit into these two towers that operate on GPU. So for instance,
our graph visualization sometimes it breaks long edges. So that conv1 is actually the input from that parameter node that's on the right-hand side. The graph would just get really messy if it drew that edge. So you can think of these things as all those variables are feeding into that tower as input. So it gets the copy of the parameters along with reading the data from the example images.
And then here on the top, we do the combination of the cost, again on the CPU, just because we'll at some point need to cross the boundary. So there's a cross boundary here and here.
And send and receive nodes are inserted in those places to accomplish that.
Right.
OK.
Cool.
OK, so now we're going to switch gears a bit, and Oriol's going to talk about LSTMs and data and model parallelism in the context of those.
Right. So as a researcher, a lot of the tools you have at your disposal actually affect the kind of research you can do. So I'm going to talk a little bit about the sort of the research that's been going on at Brain and elsewhere in the past 2 years or so. But first of all, let me describe, for example, this model that's called LSTM. It actually was introduced many years ago by Hogreiter and Schmidhuber. And the first time I saw these equations, I remember, it was 2011. And at the time, I was doing all the derivatives by hand using MATLAB, of course. So as soon as I saw these equations, I knew I wasn't going to use this model. And so I had just implemented a recurrent neural network. It was a lot of work to do the backpropagation through time and so on. So to me, that was out of the picture. I was working on optimization algorithms. So at the time, I was happy to just play with the recurrent neural nets version of the model, which is kind of it's some sort of similar to the first line of code there, or like equation rather. But nowadays, with these very powerful auto-differentiation libraries such as TensorFlow, we can really get creative and say, OK, let's define these equations. These happen to have some meaning in trying to make, for example, the derivatives flow nicely as you unroll a recurrent neural network over time. And this is one of the variants of LSTMs that we use for a bunch of tasks that I'll describe. And essentially, there's a bunch of gates, called gates, like input gate, forget gate, output gate. And then we have these 4 things that are essentially similar, but use a different shared weight matrix for both x, which would be the input at that time step, and then the recurrence over the hidden states, ht-1, and a bias. And then the LSTM has this nice property which allows the information to flow through, especially this first term here, which is the forget gate times the ct-1. So this allows you to essentially sort of accumulate a state by adding to the state, not recomputing it as you do in vanilla RNNs. And it happens to have nice properties for learning. But the important bit here is that after seeing these equations, the code actually looks fairly straightforward. In fact, I think if you count the number of actual lines that are useful in the code, there are less than equations, just because we collapsed the first 4 equations. So there's some trick to it. But this is part of the release, the open source release for TensorFlow, where you essentially have an LSTM cell class where you call it, and you pass like inputs and state. And essentially, this sort of computes these C and H's. So here, there's a very one-to-one mapping between the math equations and the code that is on Python, like the one you see here on the right. And this essentially computes all these I, J, F, O, like in the equations. and computes this C times sigmoid of F. So you can really map what you're doing on the left and on the right, which is a very nice property because a lot of these models are getting very, very creative. So that actually, why am I talking about LSTMs? So it turned out that last year at NIPS actually, so here, we presented a model that we named sequence to sequence, which allowed us to do a little more than simple language modeling using recurrent neural nets. So the realization, which was done by us and also independently by the group at Montreal, University of Montreal, not the whole group. So it was the fact that we could use these recurrent neural networks to map from a sequence to a sequence. So I'm not going to go a lot into detail, but this framework allowed us to tackle a very challenging task that had been present in NLP for many years, namely machine translation, and with a purely supervised, data agnostic, and from a random set of initial parameters, those W's that you see before, we were able to get a very good translation system trained solely end-to-end with a neural network. And we see this as a trend in the research community. We'll see, hopefully, at the conference, if you attend some of the talks and posters, you should see this as now a trend after a year of this publication.
This is an example of one of the cases where traditionally machine translation systems have a bunch of submodels that are trained independently and then sort of are combined with some code that mixes and matches the results from those models. And this is one of the pure end-to-end things that I think is going to be more prevalent in the future.
Right, and so here the key observation is actually we can read a sentence in French, say A, B, C, D, and load it into this memory V, which is the state of the LSTM, and then prime the decoder LSTM that will try to produce English, for example, prime it on V, and then produce the optimal translation. And all we're going to need to be given is pairs of French and English sentences, for example, for translation. And for this to work, actually, we found that these LSTMs, this property of keeping things in memory for a very long time was crucial. So again, this is a very active area of research nowadays. There's many groups that are innovating using RNN and LSTMs, both at all sorts of applications, and also innovating in kind of modeling. So for example, Badanao et al. Had a very cool improvement on this, which was an attention mechanism, which unfortunately I cannot describe. But again, without these libraries where you can express ideas and equations onto code, it would have been quite an undertaking to go from this idea to actual code. And there's other architectures as well that use memory, such as neural Turing machines from DeepMind or memory nets from Facebook. And all of them are kind of related and a very hot topic of research, certainly. So just here, just to give you, I mean, you're not supposed to read this, but really, I want you to note two things, that there are a bunch of applications now. Speech was mentioned by Jeff earlier, language understanding, video generation, algorithms, image captions, translation. There's a bunch of work, all of which is actually quite recent. So if you look at the year, it's almost all 2014 and 2015. And this is definitely not a complete list. And a lot of this work, actually, you can see later at the conference. So I encourage you to check it out, to look at how this sequence-to-sequence paradigm is now being taken off. And I think partly thankfully to these open source libraries that allow you to express models very trivially. So I'm going to describe just briefly, not translation because that's a little boring, but actually how we did image captionings. So I mentioned we can map from French to English. So here the idea was very simple. Let's map from an image to English so that given the image, we can give a nice caption. And the nice thing at the time I was doing this research is that it took literally one line of code to change from the translation system to this. Namely, I changed the encoder to now be a convolutional neural network, like the one I ran before with those images that I took around. And this image now kind of gets processed by a convolutional net, pre-trained, that's actually very important, and gets treated as this V vector that I was alluding to before, as the conditioning on how we would generate, for example, a description for an image like that. So here, very important to have very flexible tools for research, and you could think that, of course, computing the derivative of the word girl given the image is a very long chain rule because you have to go backwards through each of the LSTM cells, and then backwards through the CNN and so on. So definitely very good to have these tools in hand. And it turned out that, I mean, this is just the example that I showed before. So it turned out that many groups had similar ideas, not very surprising nowadays in deep learning. And there was a competition which kind of normalized the scores across several groups. And all sorts of, I mean, the people like tried a lot of tricks and so on. And the competition turned out to show that humans are still better than machines at this task by a large margin. So the rightmost column here is sort of a Turing test-like task for whether this caption is coming from a human or from a machine. And you can see that the best systems there are like around 30%. So it's pretty good, but it's not the best. And this was done on Amazon Mechanical Turk, and Microsoft organized this competition very nice, like last year, which helped a lot understand where we are in this field. So one of the things that happened is actually we submitted a paper to CVPR, and I forgot to turn off the job. And after the model trained for much longer, so in this case, I was using 5 replicas, so already I was getting some speedups from data parallelism. But it turned out that after training the model for much longer and doing a couple more tricks, like fine-tuning the image model, the same model, the same architecture, finely tuned, was able to produce much better captions like you see here. So the initial model was definitely pretty good. But the model that we actually submitted at the competition 4 months later was better. And part of that was, of course, understanding that we had to train for very long and also using better use of data parallelism and so on that we did not have time for the CVPR deadline. So there's some examples. There are some problems in this task that, for example, it retrieves a lot of captions from the training set. And it's a very active area of the research. And this has actually evolved towards question answering, videos, and so on. So it is a very cool area which kind of started just, I mean, the actual application of recurrent nets started barely like last year, even though these data sets were available actually in early 2010s. So it's kind of nice to see that we are maybe ready to tackle the next ImageNet, which instead of a single class outputs a sentence. Now, this is sort of a teaser just for this conference. We are getting quite creative on the kinds of things that we map from and onto. Initially, it was translation. Now we have this image to sequence thing. And this is sort of one of the things we are actually actively pursuing, some of us in the research community, which is mapping, or rather finding solutions or algorithmic neural nets, if you will, that will take some input and transform it to the solution of some problem like finding, for example, here, the traveling salesman problem. So here, we are treating really this as a sequence-to-sequence problem where the input is a sequence of points on the plane. And I'm going to show the neural net many examples of how to traverse these points to minimally, to minimize the length of this tour, essentially. And from this training set, we are hoping that the neural net may be able to learn an algorithm that computes, for example, solutions to TSPs or convex halls or the like. And again, here, the architecture was a slight modification of Badenau et al.'s attention mechanism, which used this idea of pointers, because in this case, actually, the number of outputs is exactly equal to the number of inputs. So it was unclear how to use a softmax and how to go beyond the number of examples you've seen during training, which is an important property. And again, to express these models, very important and actually very trivial to do so when you have a nice library. Basically, it's like 2 lines of code just to add, instead of a softmax, you add like some sort of attention function, and that's it. So check out these on Wednesday and many other cool work going on at NIPS. And then the last example I wanted to talk about is sort of one of the typical things we see that transfers research into products, and for which actually scaling up is quite important. So here we had a very silly idea of taking text from movie subtitles. So here you would have turn-based sort of interactions between people. We assume just 2 people, and we assume that each line represents a different person. So a typical training example would look something like, I got to go, no, I get too emotional when I drink, have another beer, and so on and so forth. I don't know what movie this is, actually. But it seemed like the prototypical example. And here, again, we use sequence to map from line n to line n+1, or from all the lines to the next line. So can we take the context and simply train essentially a language model over this corpus to sort of reply whenever we just ask something or interact with the system. And this we presented at the workshop this year at ICML. So this idea, it seemed that it was working well enough that we said, why don't we scale this up and try to apply this to a fraction of the emails that we see, especially on the phone, because it is certainly cumbersome to have to type answers and so on. So we just took this idea. There was a blog post recently, and we scaled it up. So again, Jeff was saying we use 16 replicas, a bunch of GPUs, and so on, due to the large amount of data that we have. And then we train the system to essentially reply. So here you see an email like from one of our coworkers, and it says, hi, we wanted to invite you to join us for an early Thanksgiving on November, beginning around 2 p.m. Please bring your favorite dish and RSVP by next week. And then the automatic reply said something like, count us in, we'll be there, or sorry, we won't be able to make it. So it's a kind of a cute application of language modeling that we hope to improve, of course, in the coming months. And so now let's go back to code and how to express this in code. So let's take this pseudocode. It's not really pseudocode. It's just a stripped version of what the TensorFlow code would look like for an LSTM. It turns out deep LSTMs are very important. So here we have an unrolled 20 time step LSTM, very typical code that we see in all these papers that open source code. And we can add depth by simply having this for loop iterate over, let's say, 4 layers of LSTMs. Now, this is almost a minimal change to the code that now allows you to put an LSTM on top of each other for each time step. And it turns out this makes the model generalize better and so on. So let's take this code. What would it take for this code now to be able to parallelize across GPUs? What would be the required change for each of these 4 LSTMs? And I'll explain why that is good, to put each of these 4 LSTMs on a different GPU.
One point I'll make is that although this model is more accurate, it's also much more expensive. Right? It's 4 times as expensive.
Exactly.
And it's very sad because now your results come 4 times as slowly.
Right.
If you don't do anything better.
So with this one line, we are telling the graph generation that these nodes should be placed on 4 different GPUs for each of the depths. So it's a very minimal code, like just one line. And of course, as researchers, we don't like to write a lot of code, so this is important. And what this allows us to do is quite amazing. So instead of having a 4 times slower system when we place these LSTMs, so here again, time is in the horizontal axis and depth is on the vertical axis. I'm showing here the model from last year's papers actually at NIPS. And I just want to make a note as well that the softmax we used then it was very large, so we actually also distributed the matrix multiplication for the softmax across 4 GPUs. I'm just showing you over there. So what happens actually when you add that line of code is that the data comes in and that square there gets computed. And then now because you have 2 different GPUs, the computation flows both forward in time, and typically you would have many more time steps than just 8 as I show here, and flows in depth. So eventually, after you run this for a while, you get 4 GPUs running precisely in parallel, computing next time step predictions. And it really made a speed up of like 6x by using 8 GPUs instead of a single GPUs. And so this is a clear instance of model parallelism, which made our step time, as I said, 6 times faster. And this was very important because initially our code was essentially maybe converging in 3 weeks with this trick. And without this trick, it would have been just not possible to write the NIPS paper. So that was very important. And a note that I want to make as well is that this was a year ago. We did not have TensorFlow. So there was a lot of pain, mostly kudos to Ilya Sutskever, who had to implement like deep C++ code to make sure like threads and would run on different GPUs and so on. So that actually took a large portion of time. And there's other tricks that we do. I'm not going to spend actually a lot of time on this. But it turns out you want to sort of batch together examples that have similar length. So in TensorFlow, we have this construct of queues, and I encourage you to like use them and because it's very useful to say, well, I get data in, I will put them in a queue, and then basically whenever the queue is full, I'm going to launch a forward-backward on a graph that unrolls for as many steps as that queue length has. This is how we do the things right now, but actually we're also working on a while loop construct, which would allow you to have a graph where inherently you have dynamic a number of unroll steps depending on the length of the current sequence that we have. And sequences are very important for us, so this definitely is a work in progress that simplifies the code a lot, and again, probably would allow us to do the next step in terms of research and constructing models. And Jeff, I think, will also explain us a little bit.
Right, so let's take a similar example of code and see what modifications you make to it to express data parallelism in TensorFlow. I'm going to express asynchronous data parallelism in this case. So this is kind of a very simple MNIST model, and the code you would use to drive it, you basically set up the model. I'm not showing the code there, but you call some routine, and that creates the model data structures and all the parameters. And then I set up a session, and then I say for 1 in max steps, then run the model each time, and print the loss every so often. So in order to actually make this an asynchronous data parallel system, the red lines are the changes we make to this code. So one of the things is we have a little mechanism that whenever we create a parameter tensor, it will spread those parameter tensors across 10 different parameter devices in this case. So that's what that first red line does. The second thing is we have a thing called the supervisor, which takes care of initialization and summaries and checkpointing and recovery. So if any of these replicas die, that supervisor is going to be responsible for bringing the system back up to a healthy state and resuming training. One of the tasks, task 0, is special and coordinates most of this activity. And then essentially, when you're using a supervisor, instead of calling session, you call supervisor.prepare session. And then you iterate over the steps. And in this case, we're actually going to keep track of the global number of steps that the model has, the number of updates that have happened across all the different replicas in another parameter variable. So we have a tensor that's a one-dimensional, zero-dimensional scalar that keeps track of the number of steps. And when that global variable hits the right number of steps, all the replicas will then stop. So that's the changes you need to make there. It's not too bad. And that's kind of the graph that gets generated by this. We now have 3 different clients that are driving 3 copies of the graph. The parameter devices, so the parameters are actually scattered across the 10 parameter devices that I asked for. And before every step, the model will fetch the parameters from the parameter devices. It'll send the gradients back to the parameter devices, and they'll get applied there, just like I was showing earlier. The synchronous version, I'm not showing the code, but it's somewhat similar in the amount of modifications you need to make. It's actually even a little bit easier because you essentially just slice the batch and then run everything synchronously. OK. So one of the things that's pretty important is to reduce the amount of data that you send across networks. So we have these send and receive nodes that have been introduced whenever we cross a device boundary. And one of the things that both our first system, Disbelief, and TensorFlow can do is essentially drop the precision on parameters and activations when you send them across the network. Neural nets turn out to be very tolerant of reduced precision. So floating point numbers, 32-bit floats, are total overkill for most purposes. So what we do is we actually introduce special nodes that convert to 16-bit floating point representation. It's not sort of the IEEE standard 16-bit. We actually just take 32-bit floats, lop off 16 bits of the mantissa, and then send that. And then on the other side, we reconstitute the mantissa by filling in with zeros. Like we probably should do probabilistic rounding or something, but turns out it works fine, and it's faster. So that's kind of a very simple graph transformation you can make that sort of halves the amount of data you send across the network. You can also implement sort of more exotic kinds of compression schemes, like in particular for activations. If you're using Relu units, a lot of the values are 0. So you can essentially, we have a little custom kernel that I think isn't quite in the open source release yet. But essentially, you take groups of 32 floating point values, and you encode a bit mask of which ones are non-zero, and then just encode the non-zero things. And often you'll have 60 or 70% zero values in a lot of these output units. Another thing that is often the case is that you can quantize your weight values and your activations in some cases for inference. You need even less precision for doing inference than you do for training. And so 8-bit fixed point, in our experience, tends to work pretty well. You just figure out the range of weights, and then you scale that to 0 to 255, and then do all the computation in terms of like 8-bit SIMD instructions on CPUs or things like that. And that's really critical for like mobile devices, because now all of a sudden you can do 4 8-bit multiplies in the time it would have taken you to do 1 floating point multiply. And that allows us to run an inception model at like 6 frames per second on a pretty high-end smartphone. Some of the things we've been describing are the distributed implementation of TensorFlow, which is not what's in the initial open source release. But we do have support for multi-device training. So there is an example of like multi-device, multi-GPU card training in a single machine in the open source release. The distributed implementation is coming soon. We essentially need to extricate our code that depends on our custom non-open source cluster scheduling system and implement a different version of that abstraction that uses probably Kubernetes container management for managing the different tasks involved in the system. There's a tracking issue you can follow if you're interested in that on the GitHub repository. Sorry, it line wrapped funny, but essentially that's coming pretty soon. Okay, so a few concluding remarks. So one of the things that really make it possible to do really good machine learning work are having that interactive, rapid turnaround time for experiments. And really, model and data parallelism are really essential to achieve that with current computing hardware. Essentially, a single GPU card, fast as it is, can't really train most large, interesting models in an hour, right, or a day. You really need something that uses many of these cards in such a way that you can get really good speed ups by using many of them. And model and data parallelism, plus lots of other things like reducing the amount of parameters in your model, encoding things efficiently to transfer across the network. All those things in conjunction allow you to get really nice performance speed ups on training really large models. And the other thing we've worked on in TensorFlow is that it's pretty easy to take the sort of the simple, straightforward single model code and produce a either synchronous or asynchronous version of that, and also to express model parallelism in that system with relatively minimal changes, as you've seen in the last little bit of the talk. And I think that's pretty important to be able to express it and then exploit it for when you want. Another thing that we've done in the last month is open source TensorFlow. We're really hoping that it kind of allows people to publish. We're going to start publishing our papers with sort of example TensorFlow code in a lot of cases. We hope that allows people to reproduce the work that we've done and build on it. We think TensorFlow is also sort of nice in that it runs on a variety of different platforms, and you can go from research idea to actually deploying that in real products relatively rapidly without sort of rewriting things. And one of the things we've been excited about, and the whole reason we open source this, is there's now starting to be a community building up around this. And the TensorFlow community is doing some pretty interesting things. Here's a few that just caught our eye. This is just a page with links, but I have a slide for each one. So when I publish the slides, there'll be links for everyone. But someone has implemented DQN reinforcement learning using TensorFlow. There's a little game, and this thing learns to go around and eat the red balls and not the, eat the green balls and not the red balls, and definitely not the orange balls. Someone's implemented, there's this really nice paper called A Neural Algorithm of Artistic Style, done by the Max Planck Institute and another German university, and it essentially renders photographs in the style of your favorite artist, and someone's implemented that in TensorFlow. There's a character RNN model that Andrei Karpathy produced a demo of, and someone re-implemented that in TensorFlow, so now you can speak like Shakespeare. Keras is a popular sort of library that sits on top of Theano for expressing deep neural nets. And the authors of Keras have ported that, so it also can run on top of TensorFlow. Someone's implemented the neural caption generator model that Oriol showed. It's not Oriol, so it's someone else, but it seems to be a pretty faithful implementation of it. There's a group in China that is translating all the documentation for TensorFlow into Mandarin, and that's pretty cool. So there's one more thing I want to mention, which is we're launching a program called the Google Brain Residency Program this year, which is basically, we're trying this as a bit of an experiment. It's sort of a one-year immersion program in doing deep learning research within our team. The idea is all of our research scientists will work with the people in the program. It's sort of a fixed one-year thing. You can imagine it as either like a pre-doc or a postdoc or a post-undergrad or something, depending on what stage in your career you are. And the goal after a year is really to have mentored the people in the program to do deep learning research and to have produced several different kind of interesting pieces of work, posted them on archive, submitted them to top conferences. And we think we have sort of a nice mix of interesting problems with which to sort of seed a lot of this research. People will use TensorFlow probably and have access to computational resources. We're looking for people who probably a typical NIPS attendee. And the application deadline's coming up in January. And then the program would start in June of 2016 and run for about a year. And you can find more information there at g.co/brainresidency. And we'll take any questions at this point.
Thanks.
Thank you. Oh, yeah, and there's microphones somewhere. Where are they? Oh, there's one there. I see it. My vision model is improving. Sure, I'll repeat it. Yeah.
One question is on when using some of the TensorFlow things, it seemed like the TensorFlow was using a lot more memory than other things. Are you doing anything to?
Yes, so the question is, TensorFlow is using a lot more memory than some of the other systems. We are working on that. There's basically a bunch of sort of compiler-like optimizations we need to do to sort of rewrite and transform things so they do more in-place operations. The other thing that will help with that, it's not obviously want to do both, but the distributed implementation can sometimes help with that because now you have more memory spread across multiple GPU cards. Question at the microphone there? Oh, sorry, there's two. Yeah.
So I have a question about data parallelism. Have you tried to do quantization at training time using a threshold on the individual gradient value of the individual parameters and only ship sparse messages when the gradient value is above a threshold and delay the other updates?
So essentially, you're asking if we do quantization on the parameter values and the gradient values?
At training time. Yes.
At training time, yeah. So for example, the converting to 16 bits and then back to 32 bits on the other side, that doesn't have to be just for activations. That can be for parameters and for gradient values going back. I don't think we've tried quantizing to 8 bits. We found 8 bits is not quite enough for most training purposes, but like we've done experiments and 12 bits seems pretty good. But at that point, you start running into issues where like 12 bits is kind of an awkward size to deal with. So 16 bits seems to be kind of the best size we're able to really deal with at training time.
And second question, sorry. So the LSTM model that you presented was written in Python. Do you have a C++ version that is wrappable in other languages? Or?
So at the moment, our Python interface in TensorFlow is the most full-featured. But what you can essentially do is define the model graph in Python and then write that model graph description. It's essentially a protocol buffer out to a file, and then load that up in the C++ program. That's often what people do. We do have a C++ interface where you can define the operations, but we don't have the automatic differentiation in C++. We're eventually going to move the differentiation into the core rather than having it be in Python, because we want all the different language front ends to benefit from the automatic differentiation support, but that's not there yet. So for now, write it to a file and then load it up in C++.
Great talk, thanks. Generally, Huawei Technologies. Actually, I come from a system background, so just wonder, this might be a very generic question. We did something for neural network a while ago, for example, even for branch prediction, if that matters. But right now, when we are looking at all these applications, they really make a lot of improvement for products, for everything. Just wonder from your viewpoint, are we in a stage of more like application research and optimization for those applications rather than theoretical improvement?
Well, I think there's actually room for a lot of kinds of work in this field, right? Certainly, there's a lot of interesting systems work on what you can, basically what should our training platforms look like 2 years, 3 years from now? What algorithms will work best? And sometimes that's a question of, like, given the training platforms that we have, that might affect what kinds of algorithms we choose. So there's a bit of interaction there. I think looking at algorithmic improvements in speeding up training are definitely interesting. And if something better than SGD comes along, that would be fantastic. And then I think there's a whole range of application areas. You saw the explosion of all the different areas that these kinds of techniques can be applied to. I think.
Yeah, I guess in that sense, on the application side, I agree that right now there's a lot more papers being done in. We applied a model that's been already defined for many years in some new data set than truly an algorithmic or like model breakthrough. However, there's some of those, and it's just that the amount of people and researchers working on deep learning right now obviously allows you for like a lot of like applications where a single researcher didn't have time to tackle maybe like some years ago.
The other thing I would say is I think people have not really started to explore applying it to prediction problems for systems, like actually operating computer systems. There's a bunch of interesting things that currently have heuristics that I think could be improved by applying neural nets to doing some of those things.
Glad to see the momentum. Thank you.
Yep.
So first of all, I just wanted to say that the system is quite amazing. I personally fall in love with it. But I have like 2 comments. So I noticed as I was doing some research that right now forward and backward paths are kind of coupled in the sense, and you can imagine there are several scenarios when you want to apply backward paths independently of forward paths. For instance, when you are backpropagating through time and you are backpropagating for different number of time steps than you are propagating in forward, or maybe you want to have separate models for the to encode and decode things. Of course, you can put it all into single model. So I was wondering if you are guys about to decouple these 2 concepts. That's let's say the first question.
So, I mean, often you can define what you want in the context of a large graph, and then pick little bits of the subgraph that you want to execute, and feed different kinds of input, and run a bit of the subgraph in such a way that you can achieve the effects that you want. But maybe we should sit down and discuss exactly what you want to do. But in general, feeding and fetching is a very flexible mechanism for sort of composing the little different pieces of the graph and getting what you want out of the system.
And the second thing is, it would be really awesome if TensorBoard would be custom, if I could be able to customize TensorBoard. So for instance, right now it's kind of predefined in the way what displays over there. Of course, let's say I'm like in my Python code, I'm defining what I want to display, but maybe it would be awesome to even integrate it with IPython in some sense or something.
Yeah,
like that.
Good suggestion. Please file a GitHub issue.
Okay, cool, thank you.
Thanks.
Just a quick question for the Python bits. Any rough time frame for Python 3 support?
Yeah, that was another thing that our internal version of Python at Google is pinned to 2.7, so we kind of underestimated the desire for Python 3 in the outside community. We're actively working on it. I don't have an ETA for you, but if you find me during the conference, I can try to get one. I think it's soonish, but I don't know if it's like a weekish or a monthish kind of time frame.
Could you please say a few words about your placement algorithm, the way it chooses to run a task on a GPU or on a CPU? So what are the considerations there?
Sure, I can do that very briefly. There's a bit more detail on the white paper in one of the subsections, but essentially we simulate the behavior of the graph starting at the roots of the graph and have a simulation for all the devices in the system and use our cost model of how long each node is going to take and the sizes of tensors that are being transmitted in the system to essentially say, well, if I ran it here, the input data is already on that device, and it would take me 10 milliseconds. If I ran it here, it would take me 2 milliseconds, but there's also 11 milliseconds of transfer time because I need to get the data from here to there. And essentially, it will then make greedy placement decisions, which is perhaps not the best thing, and essentially place data that way. And it also takes into account the hints that people give, so it only will place them where respecting the constraints people are given. We think this is an active area of research, but this is kind of the first cut.
Thank you.
Just a simple question, is bidirectional LSTM also simply supported?
Yeah, you could implement, I mean, the same way you can unroll a fixed number of steps and make it bidirectional, or I mean, we didn't release it on the open source, but we probably will soon. It's just in our research, we haven't actually used too much bidirectional LSTMs in the sequence-to-sequence framework.
I did see some changes flying around for bidirectional LSTMs, so I think they are coming.
So just a question about looping. Like it popped up during your presentation that you are working on something which would be like Tiano scan, right? A little bit of the graph that would dynamically expand. Is this correct? Because right now you rely on unrolling everything, and this is sort of unwieldy for sequence-to-sequence stuff where you have to choose which unrolled version you use depending on the batch size or the.
Yeah. So the essential primitives we have in place are a set of operations that allow us to implement a variety of different control flow structures. And in particular, we can implement conditional branches in the graph and loops. So looping constructs, so essentially a while loop. And that can be used to dynamically unroll without actually unrolling in the graph structure itself. The white paper has more details about this.
Okay, so you want to reuse what's in the white paper and what's currently not implemented, right? Because the examples don't use it.
Sorry, I didn't catch.
We did not release the while yet.
We wanted a little bit more experience with the while before we committed to that exact API, just because it's very hard to change that. But the code is actually in the open source release, so you can poke around and look at the control structure kinds of things. We just didn't want to like publicize it too heavily because we didn't want people to start depending on it before we were happy with it ourselves.
Thank you.
Yep.
Hi, do you have any plans to support OpenCL backends?
We have heard there's a bit of demand for that, but we haven't sort of prioritized that exactly where it fits with the other things. I wouldn't say it's sort of on the imminent list, but I do hear some people demanding for it. If you care about it, one way we reflect like knowing what people care about is looking at GitHub issues and people sort of following them and adding like me too to them. So that's kind of a good way to indicate that's something you care about.
Hi. So if you don't have tons of data, you're typically transfer learning to a small target data set. But TensorFlow was born out of, seems like it was born out of having lots of data and how best to leverage it. I'm wondering if you can speak to any examples where you went from solving a problem with a transfer learned model to something where you had lots of data and then TensorFlow kind of, or disbelief, was vital in doing that. I guess I'm interested in sort of like where a solution to a problem transitions from, you're solving with a transfer learned model to a
Sure. I mean, I think a pretty common example within Google is we have some visual task, and we don't have a lot of labeled data for that task. One of my colleagues is actually looking at diabetic retinopathy diagnosis. So you need to be able to look at an image of an eye and say, is this a healthy eye or a sick eye? And he didn't have that many labeled examples, so he started with a pre-trained ImageNet model, right? Which doesn't intuitively seem like it would be a good idea because it helps you detect if something's a fireboat. But it actually worked reasonably well. And he was able to convince himself that, yes, this will actually work reasonably well. And then he went out and sort of did the work to find more labeled data in the domain he cared about and improve things further. But I think that's a pretty common trend is you try transfer learning first, and then maybe that's good enough. Maybe you need to improve on it further by either sort of improving the model or going out and getting more data.
Thank you.
Yep.
Over there.
Hey, so I work on machine learning with medical data, and sparse inputs come up a lot. How full-fledged is the support for sparse matrix multiply, for example, on the GPU? Is that straight out of the box, or do I have to convert it to dense at the moment?
So in most of our work, so the question is, well, yeah, you heard the question. There's a microphone. In most of our work, we convert things to dense using embeddings, typically at the very early stages of the model, and then use mostly dense operations. But there's nothing inherent. It would be pretty easy to add sparse matrix operations as additional operations and then kernels running on different devices. That would be like an example of something that would be pretty easy to extend.
OK, and that's available in the current release?
Well, I mean, you can define new kernels and operations. Yep. So yes, sort of. But they're not defined there, I guess. Mostly because most of our work is not focused on sparse operations.
Hey, this is Subbu from Bitfusion. I've looked at a lot of things with things like Xeon Phi. Do you guys actually plan to support architectures like Xeon Phi with TensorFlow?
What is a Xeon Phi?
The Knight's Landing from Intel.
Oh, yes. So as long as your compiler generates good code for it, I think our CPU code will work reasonably well. We don't actually define different devices for different kinds of Intel CPUs, for example. We just have a CPU device, and whatever compiler flags you use to compile the kernel operations is what would sort of do that. I don't know if there's anything specific in the Knight's Landing architecture that we would need to change our C++ kernel implementation code given a good Knight's Landing compiler.
Have you guys tested it on Knight's Landing, or it's primarily Xeons?
I'm primarily Xeons.
Okay, thanks.
Would you plan to post a set of the slides anytime soon?
Yeah, I'll put them probably on my webpage. I don't know, is NIPS posting tutorial slides?
I'll find out.
Okay. They'll be posted somewhere in public. If NIPS won't do it, I'll put them up.
Hi, I have a question about data parallelism. So in the speed up numbers that you mentioned, do you use synchronous or asynchronous implementation, and what impact does it have on model accuracy?
Right. So all those speed up numbers are essentially training to the same accuracy, because that's what we actually ultimately care about. And the numbers where I showed a bunch of different models, some of those are synchronous, some are asynchronous. If you care about a particular one, I'm happy to chat afterwards about exactly which one. Most of our experience to date has been, we have more experience with asynchronous, but we're starting to see synchronous be more reasonable for some kinds of models.
But I don't think the difference is going to be very large between the two. And asynchronous is obviously a little faster. Yeah, in terms of accuracy.
I also think synchronous gives people a bit more comfort zone, because then you're sure that it's not like the weird randomness in the system that is causing things to be bad. It's just more understandable as a large batch.
So TensorFlow seems to build on top of a pretty general data flow engine. So do you have any plans to build on top of this engine for general purpose data processing tasks like Spark or something?
We don't have any concrete plans, but it's certainly the case that the underlying graph execution model is quite general and is much broader than just, say, neural net training. So we imagine that the project might evolve in those directions in the future. but we don't have any. Mostly, we're focused on making it work really well for neural nets.
Yeah, so in your earlier slide and also in your white paper, you mentioned that TensorFlow can be used in a variety of machine learning problems other than neural network. I just wonder whether you have any plan of putting some generative model or some other type of model beyond neural network.
Yeah, so like some of our colleagues have done very large sparse logistic regression models with TensorFlow.
I believe the open source also like k-means.
Yeah, there's like k-means implementations in the open source release. I expect partly, since we're a group focused more on neural nets, other parts of the community may start implementing other kinds of algorithms on top of TensorFlow's graph execution engine, and then we'll build up a little library of these things.
Yeah. Good. Well, let's give Jeff and Oriel a round of applause.
Thank you.
Thanks.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.